大家好，我是清华大学电机系黄远介。今天我要介绍介电子的波导。这回的介绍跟上回三个单元不太一样，因为上回三个单元呢，主要的目标是放在这个金属的波导上头，但是在光学频率的时候呢，这个波导的这个损耗在金属里头变得相当的大。所以呢，我们今天介绍几个基本的概念，在这个介电物质的波导里头，因为我们有个很重要的应用叫做光纤通讯，里头的光纤基本上就是一个dielectric waveguide. So initially, I'm going to introduce you a few basic concepts, and then I'm going to show you the analysis for TM mode in dielectric slab waveguide. After the first session, I'm going to talk about TM mode in a dielectric slab waveguide. But in optical communications, an optical fiber has a cylindrical geometry. So we're going to move into a topic describing a cylindrical dielectric waveguide. And finally, we're going to have a few reviews. So this is the first session about some basic physics and also basic physical picture to show you. On the left of this slide, you can see my two hands are holding a laser pointer and also a piece of optical fiber. And I can send this laser into this piece of the optical fiber and then transmit the radiation over some distance. And then the radiation will come out at the end of the fiber. This is the physical picture for the wave propagating inside a dielectric waveguide. So in general, there are two materials. One material is called core of the waveguide. Surrounding the core is a material called cladding. And in general, the refractive index for the core is larger than the refractive index of the cladding. Therefore, the wave can propagate inside the core through total internal reflection. For example, this theta 1 is called the incident angle. To have total internal reflection, the angle theta 1 has to be larger than the critical angle for total internal reflection. But if you, for example, reduce the frequency or increase the wavelength, this angle is going to reduce. And at a certain point, this angle is less than the total internal reflection angle. The radiation will just go out from the core region into the cladding. This defines the cutoff frequency of this radiation inside this waveguide. So in this bouncing figure, I want to explain a little bit the definition of the angle. This theta 1 is the incident angle in the first material for the core material. And theta C is a critical angle of the total internal reflection at this boundary. And this theta is equal to 90 degrees minus the incident angle, and this is a complementary angle of theta 1. And quite often that we use this complementary angle to describe the physics. And so be careful that don't be confused with those angles in my following lecture. And if I have a wave propagating along the axial direction where I transmit the electromagnetic radiation, in the transverse direction, the wave is going to bounce back and forth between these two boundaries to form a standing wave pattern like this. So this is a fundamental mode. You see a large value at the center. But sometimes if the bouncing angle is large, then you could create some high order mode in the waveguide. So usually we categorize the mode into two. One is with the sign dependence along the y direction. So you can see that if I describe this, the z component electric field or magnetic field by using the sign function, then you can see the asymmetry of the field pattern. And usually we call this R mode in this lecture. But if we look into a cosine solution for the transverse field, you can see a symmetric field pattern along y direction. For example, this one is like a cosine-like solution, and is symmetric about the axial axis. and we call this the even more of the solution. And propagation wave along z will have a phase constant beta because the energy will be propagating along the z direction. So no matter the wave inside this cladding area or this core area, the propagation constant along z direction is always beta, because the boundary condition require the wavefront at the boundary to be continuous. And initially, we're going to just use the XYZ coordinate to describe this slab waveguide. So the boundary is set to be at y equal to plus minus half d. On the other hand, because I have a standing wave along y direction, so a standing wave always has a phase condition, which is the round trip phase along this direction has to be equal to the integer multiple of 2 pi. So along the y direction, the propagation constant is ky. If you have a round trip distance, then you multiply this ky with 2d. And don't forget that upon refraction, there's always a phase shift at the boundary. So if you have a round trip propagation along y direction, then you have the 2 times the phase shift at the boundary. Therefore, you have a minus 2 phi right here. And the whole thing has to be equal to the integer multiple 2 pi. And this is the phase condition for standing wave between two boundaries. With this, we look into the phase at the refraction point. And if you just recall the formula from lecture 10 in electromagnetic 2 between two boundaries, then you can write down these two expressions. And these two expressions are the reflection coefficient of the electric field at this boundary. And there's always a phase shift upon refraction when you send a wave onto the interface of two boundaries. This is the incident angle, and theta 2 is the transmitting angle. You know that the Snell's law governing the angle between the incident angle and transmitting angle. So with the help of this Snell's law, you can express theta 2, the transmitting angle, as a function of theta 1. So you can always rewrite these two expressions because just express theta 2 as a function of theta 1. Then you can calculate the cosine theta 2 to be like this. So you put this cosine theta 2 into these two expressions. And now we talk about total internal reflection for the guided wave. Therefore, you set theta 1 larger than the critical angle of the total internal reflection. Therefore, the wave always bounces back with full energy at its boundary. And with this condition, you can easily see that this reflection coefficient is going to be equal to 1 because all the energy is reflected back under the total internal reflection condition. So the cosine theta 2 is a pure imaginary when you have the total internal reflection. So let's put this into this gamma for the TMO and also gamma for the TE wave. Then you can write down this expression. Just on the right hand side, you have the tangent of the phase shift divided by 2. I'm using a TE wave as the example for this expression. For the TM wave, then you have this expression. For these two expressions, you have the phase shift at the boundary. And then the whole thing is expressed as a function of theta 1, which is the instant angle inside the waveguide. And this theta c is the critical angle for total internal reflection. And the critical angle is that if you set this the theta 2 to be 90 degrees, then sine theta c is going to be equal to n2 over n1, which is the condition for total internal reflection. So now you have the phase shift at the boundary as a function of the instant angle and also the n1 and n2. Don't forget that there's a condition for the standing wave, which is the round trip phase along the y direction, the transverse direction, has to be integer multiple 2 pi. And don't forget that the ky is going to be equal to k1 sine theta because ky is the k projected onto the y direction. So this is ky is k1 sine theta. Theta is the propagation angle or bouncing angle defined right here. So now let's put this condition into the condition we just have on the last page, with this one. Just set this condition into this coefficient, and then you convert this expression into this one. This one appears to be a little bit complicated, but in fact it's very important when you analyze dielectric waveguide. On the right hand side, we just copy down the expression we have from last page. On the left hand side right here, you put down this condition into this. Basically, you calculate phi TE equal to KYD minus M pi, and then put it into this expression. And you can further convert this into a simpler expression like this by defining the complementary critical angle, which is 90 degrees minus the critical angle. And you also define this the propagation angle, which is equal to 90 degrees minus the incident angle. Then this expression is going to be more compact. On the left hand side, you still copy down this tangent KYD over 2 minus M pi over 2. But on the right hand side, now you have a compact expression, which is the sine square theta c complementary critical angle divided by square of the sine theta, and then minus 1. But there's a square root here. So this means that for this left hand side to have a solution, you need to keep this value in the parentheses to be larger than 0. Otherwise, it's going to turn into an imaginary number. Then you don't have a solution for the left hand side. So this means that always you have to keep this propagation angle less than the complementary critical angle. Otherwise, this term is going to give you an imaginary number where you don't have a solution for your ky. So the condition to have a propagation mode inside guided by the waveguide is that your propagation angle or the bouncing angle right here has to be less than the complementary critical angle. Or you can say that equivalently, your incident angle here has to be larger than the critical angle for total internal reflection, so that the wave can be guided in the core area. Once you have the this angle theta 1 less than the critical angle, you're going to have a leakage field going out from the core to the cladding, and the mode will be no longer guided inside the core. So based on this condition, we can start to use this expression and try to find out the solutions for the propagation constant and so on. We know ky is a projection of the k1, the k vector inside the core along the y direction, which is k1 sine theta. So if you put this expression into this part, just replace this theta with the ky, then you can have a transcendental equation that is a function of ky. There's only one variable ky in this equation. So you can use this equation to solve ky. On the other hand, it's physically more transparent if I replace this ky as a function of theta. Therefore, you have this expression. So just keep the right hand side the same as before, and then on the the inside is the tangent. You replace this ky with k1 sine theta. Then you have this expression. And this expression tells you that you can solve for for example, the wavelength and also the propagation angle, so that you can understand the mode inside this equation. Now let's try to do it. Let's just plot the left hand side and right hand side on the same figure as a function of sine theta. So those blue curves are the curves associated with this tangent function. And on the right hand side, you're going to have those periodical curves with a periodicity of pi, because the period of tangent is pi. So you can see the curves going from 0 all the way to infinity. Now let's try to plot the left hand side, and the left hand side is going to behave like this as a function of sin theta, because the left hand side has to be equal to the right hand side. There's an equal sign here, so this means that the intercepting point on this figure is going to give you the solutions for the guided mode inside this waveguide. In this example, we have the 1, 2, 3, 4 modes that can guide it inside the waveguide, and each point tells you a valid solution for sin theta. But this point terminating the process, this point is exactly at sin theta c. So this point is the point where your instant angle is equal to the total internal reflection angle, and this marks the cutoff of the process. On the other hand, the period of tangent is pi, so from this expression you can calculate the spacing between two curves, between these two blue curves, which is lambda 0 divided by n1 divided by 2 pi divided by 2d, because if you set this the argument of the tangent to be pi, then you're going to determine the periodicity of those blue curves on this figure. And this result over a simple way to design a waveguide to have a single mode. For example, if I just move this sin theta c bar to this point, and there's only one intercepting point, this means that I can design a waveguide which only has one mode propagating inside the waveguide. So the condition is that I set the theta c, this sin theta c bar, to this point. Then the ray curve from the left hand side only intercept with the blue curve at one point. So I can design the thickness of the waveguide to be less than this value. Therefore, I have a single mode operation for this waveguide. So this is the sort of the physical picture that allow you to design a waveguide only having one mode propagating inside. So with this, you can also calculate the cutoff frequencies for different modes, because we already know that the periodicity of those blue curves is equal to lambda 0, the wavelength, divided by 2d n1. Suppose you have the sin theta c, the cutoff complementary cutoff wavelength at this point, then you have 1, 2, 3, 4 modes inside. So let's set this periodicity of those blue curves multiplied with n equal to sin theta c bar. Then you will be able to calculate the cutoff wavelength for mode m, because this is correspond to the mode where m is equal to 0, the fundamental mode, and this is the mode number 1, mode number 2, mode number 4 on this plot. So with this equation, you can calculate the cutoff frequency for mode number m equal to this value. Suppose that now in a waveguide you operate the frequency, for example, corresponding to this point, and then you gradually reduce the frequency. This means that your wavelength is going to increase. And from previous discussion, you know that when the wavelength is increasing or the frequency is reducing, this theta 1 angle is going to decrease. So this means that this spacing, the wavelengths become larger, so the spacing between these two curves become larger. Eventually, this m equals to 3 curve will be ejected outside, because your angle, this theta angle, become larger. So this means that if you just reduce the frequency of your guided wave, then or equivalently you increase the wavelength, then the guided mode is going to be reduced. Just look at into this plot. When you increase this lambda 0, this means that this blue curve is going to be shifted toward right hand side, and eventually you eject the mode one by one. In this case, m equal to 3 mode is ejected outside this ray curve region. So this is just some physics background for a dielectric waveguide. Now let's just look into a little bit more rigorous calculation. Let's put a field Hz for a TE mode into the Helmholtz equation. And previously we already knew that the eigenvalue has to satisfy this condition. If you have a propagation mode inside this waveguide, this gamma is going to be equal to J beta, where beta is the propagation constant along the axial direction. And in the y direction, you have a standing wave pattern. So this y, this h along y direction, which is ky, is going to be a real value. The general solution along y direction is going to be either sine or cosine. And we already say that this sine solution is going to give you an asymmetric field pattern about the axis. And for this cosine solution, you're going to have a symmetric field pattern about the axis. And in the cladding region, where you have the lower refractive index, the field has to be evanescent. Because the wave is guided inside, but still you have a propagation constant along z direction, which is the beta. So in this region, outside the core area, the propagation wave in z also has the same propagation constant beta, because at the boundary, the wavefront has to be continuous. And in this cladding region, there will be attenuation of the field because the wave is guided inside. Outside this core region, there will be an evanescent wave. So this means that this eigenvalue h has to be replaced with j alpha, so that you have alpha square equal to beta square minus k2 square. So you can combine this dispersion relationship inside this core and also the dispersion relationship outside this core into one expression like this. Basically, you just take out this beta square and combine these two expressions to get this result. This result tells you that the evanescent field decaying constant alpha can be expressed as a function of the material parameters and also the ky square. And the cutoff is going to happen if the wave is no longer guided inside. This means that the alpha is not going to be real value. So between some value and some imaginary value, this alpha will be equal to 0 when right at the cutoff. When this wave is about to go out, the alpha, the attenuation constant, has to be equal to 0. So if you set this alpha equal to 0 into this dispersion relationship, then you can prove that this condition will happen when this theta 1 is equal to the critical angle for the total internal reflection. Or alternatively, this sine theta, the propagation angle or bouncing angle, is equal to the complementary critical angle. So this basically prove again that to have a guided mode inside this dielectric waveguide, the propagation angle, or if you prefer, let's just look into this instant angle, that has to be larger than the critical angle for total internal reflection. And right at the cutoff, this angle, theta 1, will be equal to the critical angle of total internal reflection. 所以在这个小节里头，我们介绍了一些 dielectric waveguide 的基本的物理概念跟物理的图像。其中一个最重要的概念就是里头传播的波的 instant angle 必须大于这个边界上头的 total internal reflection 的 critical angle。这时候呢，这个波才会在这个 waveguide 里头不断的弹跳，然后呢往前传输。那一旦这个条件破坏了之后呢，这个波就会跑到外头来，这个能量就没办法在里头保留下来。另外呢，在一个这个 y 的方向上头，也就是 transverse direction 上头的话，因为它是一个上下弹跳的一个概念，所以呢会有 standing wave 的 pattern 的形成。那 standing wave 的话呢，都必须满足一个相位的条件。这个相位就是 round trip phase has to be integer multiple 2π。那这个 round trip phase 呢，包含两个部分，一个呢是在波在 y 的方向上头传播的时候呢，自然这个累积的一个相位就是2d，也就是 round trip 的这个 distance 乘上 ky。另外呢，在这个边界上头，一旦有全反射的产生的时候呢，这会有一个这个边界的这个 phase shift， 就是 phi T mod 跟 Tm mod 的这个值不一样。那把这两个相位都把它加起来以后呢，那这两个相位呢，如果是一个 round trip propagation 的话，在 y 的方向上头必须是2π的整数倍。那这个边界条件上头要求就是我们在 z 方向上的 propagation constant 呢，不管是在 core 或者是在 cladding 里头都必须是一样，因为在这个边界上头，这个波前是连续的。那你如果把这个guiding condition 跟phase condition 把它给放在一块，然后做一下分析的话，那这个分析的过程可以告诉你，在这个 waveguide 里头的 mode number、cutoff frequency， 还有这个 mode field 的这个长相等等都可以从这上头解析出来。那这就是下几节我们会做的介绍。谢谢。